Let's take a look at section 4C. So this is where you start to get to the really common questions, and it uses everything we've done so far. So in a nutshell, this is the chapter. So often it will talk about a rigid body. That's this rod here, this plank, okay? Plank, could be a plank as well. There you go. It will say that it's in equilibrium. So equilibrium, what does that word mean here? It has two consequences. The first one is one that you already know. Forces up equal forces down. Yeah. Forces left also equal forces right. But that's kind of obvious, and you don't really use that property. If you have a seesaw, no one's pulling the seesaw away to one side or the other. So that's sort of almost unspoken. But the up and down makes sense. It's not sinking into the floor or levitating away upwards or something. So up and down is equal. That property there is quite useful for solving harder problems later. It seems really obvious, but that's what you use. The one that's new, though, and we've talked about already, is the resultant moment. In other words, the turning is all zero. So all the forces that way equal all the forces that way. Clockwise equals anti-clockwise is another way you might want to think of it. So we normally use both of these to solve problems, and it's not always obvious which order you use them. Okay, try to use the top idea first, up equals down, but sometimes you have to use moments, the moment part, then the forces. There's no guarantee about which order to answer them. Here's our example then, and this is really, really common that there's something in words and there's no picture. So you have to be able to turn words into pictures. There's no way around it. You have to practice until you can do this confidently. Lewis and Tom are having fun on a uniform seesaw. Uniform means its mass is concentrated at the center. You will see this on the diagram in a moment. It means I will draw its weight symmetrically, it's right in the middle. The next section, we talk about things that are not uniform, which tends to be a bit more difficult. So this one is uniform. Normally, you talk about a uniform rod, a uniform seesaw, something like that. And it has a mass. You also need to be doing this, underlining. This is important. We'll talk about this later as well. Lewis weighs 70 kilograms and is 10 centimeters from the pivot. Well, I kind of know there's a pivot or a fulcrum. There's something to go around. Tom is 8 meters from the pivot. Well, hang on. I had weight and distance, and now I've only got distance for Tom. So that's probably where the question's going. The seesaw remains horizontal. Right. The seesaw remains horizontal. This is another way here that they are saying is in equilibrium. If it weren't in equilibrium, it wouldn't stay horizontal. So this is about the rotation, really. But we just talked about this. This is equilibrium, really. Okay. So how do we solve this? Well, first of all, we need a diagram. So I want you to picture this and really have a go at what it would look like, and think about what you would draw on your diagram to compare. Okay, so I'm going to assume that you've done that. So this is what I would expect to see. Something like this. And this is actually not finished. Sometimes a question in itself is draw a force diagram. Well, that's not a force diagram because there's no forces. We sketch the forces. So this might surprise you. We've got 70 kilograms turns into 70 G. Okay, so that's the force. I personally like to do this when I'm finished, so you know not to reuse that number. 20 G and this pivot are not in the same place. Who said that they were? Think about it. We know that Lewis is 10 meters away, and we know that Tom is 8 meters away. So the pivot's not in the middle. It doesn't have to be. Yeah. What is in the middle and what must be in the middle is the mass of 20 kilograms. And that's turned into a force of 20 G. Okay? Because it's a force diagram. It's not a mass diagram. It's a force diagram. The rod itself has an actual mass. So it has a force. That's kind of different because sometimes in year 12, we ignored that. Yeah? Like we ignored the string. We said that the string is light and inextensible. Well, here for planks, for rods, we need to include that. As soon as I've got these numbers, good practice as well is get rid of that. Uniform, yep, I've tackled that. 70 kilograms, done. 10 meters is on there, done. If you do this, you'll be able to spot things that you haven't used in the question. Tom is 8 from the pivot. Well, using all of that together helps you place this bit here, okay? Now, Tom, we never found out how much Tom weighed or what his mass is. So I would probably call him M because you don't know. If you call him M, then you can draw mg because you need all of your forces for your force diagram. What else is there that might surprise you? Well, this one here. Why do we need this one here? Think about what would happen if you had all of these forces down and you didn't have a force up. Why is that nonsense? Well, it's nonsense because the rod is going to accelerate into the ground. There must be something. There's all these people sitting on it and it's heavy. It's 20 kilograms. There must be something stopping it from going into the ground. So that's why you need that reaction. Okay, so we've got some choices here. So we're going to do some moments, and based on what you did in A and B so far, you've probably got an idea. So I would say most of you now would be thinking, well, it's about equilibrium, so it's about anti-clockwise equals clockwise. That's probably what most of you are thinking about. And you're probably thinking of doing it from this pivot. Well, you can do that. I mean, let's have a look at the options. That is one way that you could do it. So if you did that, that's put down here as method 1. Okay. So if you do from the pivot, you would say, well, that's 10 away and it's 70G. So 10 times 70G and it's anti-clockwise. This one here, well, that's 1, isn't it? 9 plus what is 10? It's 1. So it's 1 and it's 20G. And that's anti-clockwise. That's anti-clockwise again. And you could say, well, those together must be equal to this one. And this is 8 away and it's mg. Okay? And that makes sense. So you could work out the 90 kilograms there that way. Tom's mass should probably be the A question, and the reaction force should probably be the B question here, by the way. Okay? So you can get the mass there, and then what can you do at the end? Well, if you know that this is 90G, we said moments, that's one part of the question, but also up equals down. So what's up? Up is R. What's down? Down is 70G, 20G, and 90G. So it'll be 180G, which is the same as this number. So that's one way that you could have done it. Okay. However, later on you will see it's normally better to take moments from one end of the ladder. And this will seem very unusual to you. But the idea is with moments, it doesn't actually matter if you take moments from like either side of your pivot or if you take them from one end of the ladder or seesaw or whatever it is. There is some techniques that we use to find the best place to do it, but it's normally what from one end you will do this. So we can take the moments about Tom. So in other words, we can go here and we can think of how far away everything is from Tom here. Well, that is 18 meters, and it's perpendicular to 70G. So where's that? Where's that on here? There you go. 18 times 70G anti-clockwise. This is from Tom's perspective. we can do the same with the mass of the ladder and its weight. So we can do 9, and that's perpendicular to 20g. So 9 times 20g. Anti-clockwise, anti-clockwise. And that must be equal to 8, and that's perpendicular to r. That must be equal to 8r, because the anti-clockwise must be equal to the clockwise. If you do it that way, look, you end up finding out what r is first, and then when you find out what r is, you could do the up equals the down. Now, you're going to read this, well, you're going to see this or watch this, most of you, you're going to think, no, I'm doing method 1. You are for now, but trust me, you will be doing method 2. Okay, method 2 is more useful, is often asked for more in questions, and you need to do it that way most of the time. So, interesting point here about moments. Doesn't always have to be from the support, because sometimes there won't be one support, there'll be 2 supports, or you won't be able to do it because there will be other things that you can't work out. So moments, we can do them from the ends of the balances as well. Work example, let's do one more, nice and quickly. So a uniform beam of mass 40 kg and length 5 rests horizontally. Okay, that sounds like equilibrium to me. On support C and D. Look, there we go, 2 pivots. AC, well, AB is the whole ladder, so AC must mean from the left to the first pivot is 1 meter. Yeah. That's already on my diagram, so I'm going to cross it out because I can see that already. And DB, okay, I can see that too. When a man of 80 kilograms stands on the beam at E, the magnitude of the reaction at D is twice the magnitude at C. What are D and C? D and C are the pivots. The magnitude of the reaction at D is twice at C. So it's not the same. They don't provide the same support. D has to do twice the work that C does. Well, let's label these forces on first. 40 kilograms. The ladder is 5 meters long. So X. Why have they called this X? Let's try and work that out. When he stands at... Okay, I don't know. That distance just seems to be the man, and I don't know where the man stands. Find the distance AE. Find the distance from the end to the man. Okay, so the mass, I'm going to draw the weight of the beam as 40G. So the beam itself is in the middle, which is 2.5, because the thing is 5 meters and it's uniform. So if it's uniform, it has to be in the middle of the 5 meters, 40 kilograms. So that becomes 40G. There we go. All of that information is to place that one. That's not the man, that's the beam. Rests horizontally. Well, I will need to use that. I will need to make things equal and so on. The man is 80 kilograms. Okay, so the man is 80G. And I don't know where the man is standing. That's the whole question. So I'm going to just say that he is X. Now, how do you know to do this? How do you know to call this distance X? Well, the question is about A to E. So it's probably just a good idea to call that distance X. You need to do something with distances anyway. Otherwise, you're not working with moments. Okay. The reaction at D is twice at C. Yeah, because we've got forces down, but where are our forces up? That's twice that one there. That's R then, and that's 2R. Yeah, that's what we want to do. So these are all of the forces up. These are all of the forces down. Have I missed anything? No, I've done that. I've done that. So what sticks out to me? I could find R. I could find R if I wanted to, couldn't I? All of the up has to equal all of the down. I feel like that might be useful. So R plus 2R, 3R equals, well, that would be 120G. Or in other words, R equals 40G. Now that could be really, really important, because if we're looking at all of the forces and we have unknowns twice, we won't be able to do it. So that's why we might need those values there. Distance, A to E. Well, if it's a distance, up and down is not going to be useful there. Moments. So moments, and because I'm talking about A to E anyway, I'm going to do my moments from point A. So moments at A. And I'm going to work from A away, and I'm going to look at all of the forces, and I'm going to say that anti-clockwise equals clockwise. So let's do anti-clockwise, and let's do clockwise. So from A, the first one you hit is R. R is anti-clockwise because it's to the right and up. So that will be 1 times R. And R is 40G. What's the next thing? The next force is the weight from the beam. To the right and down, that's clockwise. So that is 1 meter, 1.5. That's 2.5 away, 2.5, and it's 40G. Okay, so I've done that one. I've done that one there. What about the man? The man is mystery number away, but he is 80G. So he is 80G times X, which is the mystery distance away. Done that one, done that one, done that one. So this one here, how far away is this? Well, that's 1 meter from the end, and the whole thing is 5 meters, so it must be 4 meters. So 4 meters away, and it's 2R, it's 2 lots of 40G, it's 80G. Well, because the beam rests horizontally, all of the anti-clockwise moments are equal to the clockwise moments. So I can do that. 40G plus 160, it's 160, 320, so 360G is equal to, well, that's 100G plus, how could we write this? I don't know. I don't generally like writing 80GX, but I suppose we can. Take away 100 from both sides. So that would give us 260G equals 80GX. Look, the G's cancel. So 260 over 80, or 26 over 8, whoops, or 26 over 8 is our distance. 26 over 8, what's that going to be? 36%. It's like 2 point something, okay? Which also works because the beam is 5 meters away. Okay, so we can find out how far away the man is, the 80-kilogram man is on this beam. Okay, so I would really kind of encourage you, before you have a go at the test your understanding, to try and replicate some of the techniques there, like underlining all of the key words. Because if you miss something, unfortunately, your force diagram will be wrong. And if your force diagram is wrong, your solution will be wrong. So it's really worth taking some time, making sure that your force diagram is perfect before you move on. Then, well, lots of the things were the same, clockwise and anti-clockwise. How did I know to do this one before I did this one? It's just practice, lots and lots of practice. It would not have been the end of the world if you had done moments first and then thought, oh, I need to work that one out. But it's something that should go through the back of your mind. Up equals down and anti-clockwise equals clockwise. Both of those ideas are useful. So I'd like to pause the video and have a go. And you know, the challenge is only a challenge, okay? That's not what I'm expecting you all to do. One thing I would say here is the way that the diagram is labeled in terms of 0.2 meters, 2 meters, and so on, you don't have to label it the same way if it's confusing to you. Yeah, you need to make sure that it makes sense for you when you're trying to solve it. Steps to success there at the bottom. Pause the video and have a go before I reveal the answers. Okay, so there are a lot of similarities with this one. Magnitude at D is twice the magnitude at C, so you should have had something like this. 50G, not 50, but 50G. Remember, it's a force diagram. Weight is a force. And I think, is that it? A uniform, horizontal, and dB, given that the reaction, okay, from that, then you should be able to work this one out. So your force diagram looks like that. Notice how they've worked out the distances. They've said if that's 0.2 and that's the middle, well, that will be 1 meter in, so it's 0.8 more. If that's x, well, this part and this part together make 1. So 1 minus x plus x is 1. That's sort of how they've done that. They've done their moments from C. Okay, they've done their moments from C, but I think you can do your moments from anywhere on this one. You should get that this number here is 0.6. Okay, so there's probably a quicker way to do that one. For the challenge, if you did have a go at the challenge, you have to draw a new diagram because it says it is now moved. As soon as you start moving supports on the diagram, you have to start with a completely new diagram. Okay, but if you did that, actually it was sort of the same question. So you now should be ready to have a go at exercise 4C. So remember, vertical forces are equal and moments are equal to. Okay. Total clockwise equals total anti-clockwise. That's normally the way that I do it. And I also do vertically up equals vertically down. If there is more than one pivot, the question will likely make you do both of these things. Yeah. Something else to watch out for here. It's very, very common to have the R and then 2R or something like that. Please don't assume that the supports are the same. They don't have to be the same. There's no reason why they would be.